As we flow into our next concept, let's ask when we have a wave, what's moving and how is it moving? So we see the bump moving down the line. That bump gets started and just goes straight down the line. We see that moving, so we know that the wave is moving. It's got speed that we call the wave speed. That's equal to f times lambda. That's constant. If that speed is constant, then the acceleration of the wave is equal to 0. Okay, but the wave is only moving because the string is going up and down. So the string is also moving. Specifically, each element of the string is going up and down. So each little bit, if you focus on one green dot, you'll see that that green dot alternately goes up and down. If you stare at it for a little bit, you'll probably see that the velocity is not constant. So to distinguish between the wave speed, I'm going to call the velocity of the element of the string Vy. That's called the transverse velocity. That's not constant. If the velocity is not constant, then the acceleration is not constant. All right, our next little bit now will be to look at that velocity and acceleration. Let's now set about finding that transverse velocity. So, very quick recap. The wave travels to the right with speed v. That's equal to f times lambda, or omega over k. That's the bump going down the line. The bump goes down the line because each little bit of string, so each element of the medium, a part of the medium is called an element. Each of those little bits of string goes up and down in turn. That has a symbol Vy, and that stands for transverse velocity. So let's see how we find the transverse velocity. Well, we know that the equation for position, or the height of the string, is amplitude times cosine of kx minus omega t plus phi. This is for a wave moving to the right. The velocity for each part of the medium then would be the derivative of the position. So the transverse velocity is equal to the derivative of the position with a function with respect to time. Except it's kind of a special derivative, and it's called a partial derivative. We see that the height y depends on two things. We only want to take the derivative with respect to one thing. When we take the derivative with respect to one thing, that's called a partial derivative. You may or may not have seen this in Math 1001. The way we deal with a partial derivative is we take the derivative with respect to time and we treat everything except time as constant. So when we run into an x, we're going to treat x like a constant. So let's see how exactly it is that we do that. So we're taking the derivative of y, which is a times cosine of kx minus omega t plus the phase constant phi. All right, in derivatives, our constants can come out front. So a comes right out front. We've got the derivative with respect to time of cosine kx minus omega t plus phi. Okay, the derivative of cosine is minus sine. I'm going to take that minus right out front. Got the same argument, but we have to apply our chain rule, which means we take the derivative of the argument. Okay, almost done now. Let's just look at the details of this guy. So the derivative of this bit, the derivative of kx with respect to t, that equals 0 because k is constant and we're treating x as constant. The derivative with respect to t of minus omega t, that's minus omega, And the derivative with respect to t of the phase constant phi is 0. So this whole expression just has a derivative of minus omega. Let's fill that part in. So I've got minus a times sine, I'll write small so I can fit it all in, minus omega t plus phi times minus omega. Okay, put it all together in one line. Vy, the transverse velocity or the velocity of one little bit of string, is minus a times minus omega, that's a omega, times sine of kx minus omega t plus phi. It's got the same argument as the position, but this one goes as a sine instead of a cosine. The next thing we'll do is figure out what's the maximum and minimum. So for maximum transverse velocity, Vy, it's a function of x and t, so the speed is a function of position and time. It's equal to a maximum. We might call that Vy maximum. If our sine argument, so sine of kx minus omega t plus phi, if that's as big as possible, we know that sine varies between minus 1 to 1. To get our biggest possible velocity, that would happen if our sine term is equal to plus 1. And that gives us a maximum velocity of a times omega. Same result as we had with simple harmonic motion. So we just found the velocity of each bit of the string. We could also find the acceleration for a part of the medium. This would be called the transverse acceleration. So that's the acceleration of each bit of string going up and down. We know that velocity is the derivative of position. Acceleration is the derivative of velocity. So we're doing d by dt. Again, we're taking the partial derivatives of a times omega times sine kx minus omega t plus phi. So we take our a outside, take our omega outside. We've got the derivative of sine. The derivative of sine is cosine with the same argument. Going through this just a little bit more quickly because it follows the same as previous. Then we still have to do our chain rule, which says we're taking the derivative of the argument. And the derivative of the argument, again, is just going to be minus omega. So I've got a times omega times cosine kx minus omega t plus phi times minus omega. So my transverse acceleration is minus a times omega squared times cosine kx minus omega t plus phi. Okay, what interesting things are we going to say here? Our transverse acceleration, we could also say, is minus a or minus omega squared times a times cosine kx minus omega t plus phi. This part, you might recognize that as just being the height of the wave, minus omega squared times y of x and t. That's the same kind of form that we have in simple harmonic motion. For transverse maximum acceleration, that would happen when your cosine term is equal to negative 1. And would give us a times omega squared. Remember, cosine can go between plus 1 and minus 1. Those are the two extremes. If cosine term was equal to plus 1, we'd have a negative acceleration. I'm a little bit pedantic. I would argue that that's not a maximum. So I think you get your maximum when your cosine term is equal to negative 1, and it gives you a omega squared. Then I think the very last thing I'm going to say here is lots of times we're going to do problems where we want to find speeds or accelerations or positions. It might be a little tempting to use kinematics because you're real familiar with those and you practice with those for months in high school in 1020 and 1050. But remember, kinematics doesn't apply to variable acceleration. It's only constant acceleration. So AY is not constant. It actually goes as a cosine, so it's always changing. If your acceleration is not constant, you can't use kinematics. So that's just a little pitfall to be careful of. As a homework exercise, you should try and find the transverse velocity and the transverse acceleration for a left traveling wave. The only difference between the left and rightward traveling wave is in the equation for position, we have plus omega t for the left traveling wave. We have minus omega t for the right traveling wave. So start with the equation for position, find v and a. I won't do it in a video, but I will post the notes if you want to check your work.